questions? Okay, that's simple enough that we can actually build this and it will work reliably, right? So it's just a matter of creating these mechanisms and making sure that all processes are doing the same thing. That's why we get the code as part of the operating system for every process so that they can do the same thing. All right, now that we look at that, I don't want to spend too much time on this. So in a monolithic operating system, we don't have this notion of processes. We already talked about that a little, but that's what your author, for some reason, gets into it at this point instead of earlier. We talked about it earlier, but so when you're going through the readings, just understand that even though we don't have processes in a monolithic operating system, we still have this division between operating system code and application code. Okay, so your application code will be sitting on top of the kernel code. And your application code in monolithic systems, by the way, there's still some out there. And the monolithic operating system may actually have several applications, but they're really still one. What you typically have done is you divided your application into different areas of code, just like you create different objects or you create different functions or methods today. You can actually create different series of subroutines that you then load as application code on top of the kernel in the monolithic operating system. And that's what your author was trying to say here, okay? So don't get too hung up on some of the symbolism he uses, because the reality is it's still a single application, even though it's broken up into different subroutine sections. Just like functions and methods and objects. Now, in a multi-programming operating system, just like we were talking about, is that you do have your process. But just as we were talking about earlier, process also includes functions that are part of the operating system. There are still some routines in the operating system that are part of the kernel or microkernel process itself. Okay, and those very basic routines will still need us to call or invoke that particular process into the run state to do some work, but typically we minimize that as much as possible, and it's usually involving any types of traps that you have set. Yeah.
Is that why like low system calls like that are isn't really like considered expensive operations? It's because we have to invoke a new process rather than just be like bundled in the executable?
Exactly. Anytime you have to do a context switch, that's when it gets really expensive, because a context switch is the set of work that you have to do to swap between to switch between one process and another, to and from the run state. Okay, so we try to minimize that. Try to minimize context switches. And by the way, you can look at these statistics on your machines, whether it's Windows, Unix, Mac OS, whatever. You can actually look at your system statistics and see these numbers for real and see what's going on in your machine, see how hard or efficient your machine is working for you. But yeah, we want to minimize that, recognizing that we do have to do some sometimes. All right, so I think we covered that one. So now let's talk about the process image itself. Remember I said a little bit later we'll talk about how we organize the process in memory? That's what a process image is. Okay? To do that, we need to understand the different parts of a process. And I've named them up here. And I have a graphic to visualize this, but I'm going to go ahead and put that up here anyway. There is the user stack. There is a kernel stack. There is what we call a text region. So sometimes referred to as VSS or text region. And then there's the PCB. What we call the process, no, not the PCB. I want to show that yet? Did I put that in this slide? Yeah, I did put PCB here. I want to introduce it a little bit differently to you. Okay, and so the context of a process are these four areas here. So the text region contains all of the instructions for this executable file, from this executable program file that is now part of course, the process. So when we load up memory with the instructions that are going to run inside your CPU when this process runs, that is all loaded into the text region. So there's all your instructions. And then we have the two static areas. User for when your process is in the user run side, kernel for when the process is in the kernel run side, not the run state. Okay, so those are the stack regions where they're putting the data, where your process is building data and taking data from itself as it's calling functions and returning from functions, right? So those are your stacks. This region here that is inside of this thing that I call the PCB and drew kind of funny is where, yeah, they went black. Is where all of the state information for this process is going to be stored. And I have a slide I'll show this, but things like the process ID, the parent process ID, what state this process is in at any given time, all of that kind of information about the process is in this region here. So the process context are these four regions. Every process will have four regions. They will all be different sizes depending upon that process's needs, except that this region here is fixed. And this region here is memory resident. Memory resident meaning that that particular region of the process is always in main memory. There is a single PCB that the operating system maintains. That PCB has the process ID of every process that this operating system can ever have. So it'll have processes that have been created and not from created to zombie states, and it's got processes that don't exist. Okay, this PCB table was always memory resident. So that particular region is always in main memory, even if my process is in ready swapped or blocked swap states. That part of the process is still in main memory. And you'll see why when you see some more of the fields that are in there, because in order for any process to determine, oh, this next process is the one to run, it's at the head of the ready state, ready queue rather, right? Well, all the information about that process is in there, including a pointer to main memory to these other regions. Kind of important. Okay, so that was memory resident. All processes will have these four regions with them for those specific purposes. Okay, process control block fields. Okay, as I mentioned, the process ID is one of the fields, the parent process ID, but it also has that program counter. Remember we were talking about every process needs to be able to have a copy of its program counter, because if I'm going to do a context switch and swap the process out of main memory, switch it out of the run state, then I need to know what the contents of all of its registers are, including the PC register. So the PC register will be here. This program status word, which contains the state of the processor after the current instruction, right? Remember the PCW? Probably thought you weren't going to see that again after you had your computer architecture class, right? Hello, it's back. So process, PC, PCW, all of your registers, because when I restore your process back into the run state after I finish swapping it out, okay, it needs to look like it never left the CPU. The only way we can do that is to restore all of the registers to whatever was in them at the time it did that last instruction. So we're going to have some other things in here, such as time when the process started, its time quantums, child process IDs, things like that. It's going to have all of those fields inside of it. It's also going to have, this is important, pointers to its other regions. Right? It needs to know where its text region is. It needs to know where its kernel stack region is. It needs to know where its user stack region is. Okay? File management. Unix Linux system use something called a file descriptor table. When your process is created, it's going to create this table. Size of which is predetermined by the operating system. And when your process is first created, it's really important. Okay? All this is important, but this isn't written down very handy for you. When your process is first created, it's going to open up 3 files for you. When I say it, that would be the fork system part of the system call, the fork system call, creating a nearly identical child process of the currently running process. Regardless of what the program was running in that process, the new child process from this fork system call is a nearly identical copy of the currently running process. Is that testable? You bet. One of the things that's nearly identical, but slightly different, is the file descriptor table. So the fork system call is going to create this table, and these first 3 files that it creates are very special files. They have names such as standard in, standard out, and standard error. So when you're using your system calls for read, writes, puts, gets, all those kinds of stuff, and you use standard in, standard out, standard error, this is where they're identified. And they're identified as file descriptor 0, file descriptor 1, and file descriptor 2. The order does not change. The order is always this: standard in, standard out, standard error, 0, 1, and 2. Very powerful tool. We're going to see why later. Keep that in mind, write that in your notes, live it, breathe it, whatever. Very important. Okay, so file management, it's also going to know things like what is my current working directory, CWD. Right? Some of you have done the PWD command on your shells, which is actually a program that runs that prints your current working directory for you, and a listing, if you want to do listings. It knows about permission bits, all that good stuff is all part of your PCB. It knows who you are. It knows who is the owner of this process by user ID and group ID. Okay. So creating a process in terms of memory now. When the process is creating, it's going to go through the PCB. And what it's going to do is it's going to look for an entry in the PCB. It probably has some pointer here saying, oh, my last entry was here at process ID 66521, right? And so you do a fork system call, and it's going to look for the next process ID that's available. So it simply scans the state of the next entry in the PCB. If it's 0 through 9, which create through zombie, it knows there's a process that exists that's using that entry. It'll just go to the next one. So it's looking for a null entry for state info. So as it finds a null state process entry in the PCB, it says, aha, that's your PID. I'm going to use this entry in the PCB for this new process I'm creating. So the process that was running that did the fork system call, it'll be told, here's your child process. You just created this child process. Its process ID is whatever that entry is. And then it changes that state information to create 0, and off it goes. Okay? So it's going to assign a process, a unique process ID using that model. By the way, yes, it is modular arithmetic, right? Because once you get to the end of this table, that doesn't mean we're out of process numbers, right? Because processes come, processes go. So we simply go from here back down to 0, and we just continually look for some state that is set to null. Then we do this next thing. We create space for the process. U area. Everybody know what the U area is? This is the U area. These three regions, user stack, kernel stack, text region, together, collectively, are the U area. The U area is the part of your process that can be swapped out of main memory into that swap partition when it's in the blocked when it's in the block state. Transition to blocks swapped. Or if it's created in the ready swapped state, it's going to create the U area right into the swap partition and not bother main memory with it at that time. Okay? But this is the U area. These three regions here. I said that when you do this fork system call, you are creating a nearly identical copy of the running process, right? I know you'll never forget those words. Nearly identical means that these three regions are identical. Well, almost identical. This region's identical, almost. This region's identical, definitely. This region's identical, almost. Almost, because fields like this one, process ID, parent process ID, they're going to be different between the parent and the child. Because every process is going to have its own unique PID depending upon which entry in this PCB table it gets. Likewise, the parent process isn't going to be the parent of itself, right? The child process will have the parent, the process ID of the process that created it, set to its parent process. Which means when you're studying that fork system call, you really want to take a close look at that return value. Because that return value is going to be one of three things. It's either going to be 0, a positive integer, or a -1. If it's a -1, we've got some serious problems. Because -1 says a new child process couldn't be created. And if the operating system could not create a new child process, then that means we're either out of entries, our PCB is full, in which case we can't create any new processes, we're in big trouble. When we ran out of memory, are no longer managing memory, in which case we're in big trouble. In other words, if it's a -1, this system is going down, it's in the process of going down, okay? Still check for it, because we're always checking for errors, but that's what a -1 on a fork system calls tell you. You could create a child process, the operating system is in serious danger. Oh, so it could be a 0 or a positive integer. Let's look at the positive integer first. If the fork system call returned a positive integer, that's a good thing. That's exactly what you wanted. And that positive integer, by the way, is the process ID of that child process you just created. And guess what? As the parent, that is the only time you will ever be given that ID number. So your parent process, if it gets a positive ID, positive integer, that is the process ID of that child process you just created. You will never see it again, so you better save it. If you care about the process ID of your child process you just created, you want to save that, because that's the last time you're going to be given that information. Then the third thing it could be is a 0. 0 is also a good thing. 0 is what you would see if you were the child process. That says, oh, I was just created. I'm a new baby process. I'm a child. Right? And that's good, because you as programmers are going to be writing code looking for this return value. And you haven't done an exec yet. You've done a fork system call. And so you as programmers have to determine that code's coming back and it's going to execute after the fork system call for both the child and the parent process. The child and the parent are going to look at that very next line of code that you wrote here. Okay, so if you care about the child doing something different than the parent does, this is where you're testing to see if it's 0 or a positive integer. If it's 0, you're the child. If it's a positive integer, you're the parent. Do that test if you care. If you don't care, they're all going to do the same thing, and that's fine. But that's one of the very powerful mechanisms with the fork system call that you need to be aware of. Okay? So nearly identical copy, because most of these fields, most of those regions are going to be identical with a few exceptions. A couple of other exceptions are things like the time quantum, because the child process should get a full time quantum. It shouldn't get just a little bit left from the parent, right? So we don't want the child to have just a little time quantum. We want the child to have a full time quantum. So we'll reset that. Likewise, we'll reset signals for the child process, reset time used, a couple of things like that. And the other thing that's different, of course, is because this system call is on the stack, then that means, in the kernel stack specifically, that means that value is different here inside of the child's kernel stack than it is the parent's kernel stack. But everything else is the same, right? Yes?
Is the CPU time interval an amount of time, or is it like a drop dead time?
No, the CPU time there used is just it's a continuously added function. So we can tell over the life of your process how much time did the use of the CPU. So it's just accumulating. So the child process, since it's new now, we want to reset it to 0. Yeah. It doesn't suffer from its parents' sins, right? So actually I did say that. Set up linkages, update the PCB. We talked about the states. And then there's this accounting stuff that's going on as well. We talked a little bit about the accounting stuff, how much time the CPU we use. We'll reset all that stuff as well, okay? So that's what we do for process creation. Questions? Okay, well, let's take a short 10-minute break here. Let's resume.